Welcome to Lesson 5 of Module 2. In this lesson, we will walk through a RNN example with a practical dataset. In particular, we will cover using PyTorch to implement an RNN. Let's consider a real-world problem faced by an online store, the need to offer only the best products to its customers. To achieve this, the company must identify whether customers are satisfied with the products that they offer. This could be solved with ML by creating a model that implements sentiment analysis based on customer reviews. This lesson will examine one possible solution, step by step. The first step is to implement a recurrent neural network model. The PyTorch deep learning framework will be utilized to build and train the RNN. Additionally, a practical dataset containing customer reviews will be employed to train and evaluate the model's performance in sentiment analysis. We'll walk through some example code. First, PyTorch libraries must be imported, along with submodules and classes to manipulate datasets and tensors. The Torch text package contains data processing utilities and popular datasets for natural language processing tasks. It includes the vocab class, which defines a vocabulary object used to map words or tokens to numerical indices. The getTokenizer function from the torchtext.data.utils module generates tokenizers for splitting a string sentence into individual tokens or words. Additionally, TorchText provides the glove class, which allows you to load pre-trained word embeddings like glove vectors. The code snippet on this slide reads in a CSV file and assigns it to a pandas data frame object that is named df. The head method is then called on this data frame object to display the first 5 rows of the data frame and the column names. Next, basic exploratory data analysis should be performed. Some steps include looking at the value counts to check for imbalanced labels, identifying missing values, and handling those missing values by filling them in, for example. The dataset should be split into training and validation sets. To do so, we use scikit-learn. Here, we separate 10% of the data for the validation dataset using the train_test_split function. The shuffle parameter is set to true to randomly shuffle the data before splitting, and a random underscore state of 324 is provided for reproducibility. The code assigns the resulting training and validation data to separate variables for text and labels. The text needs to be transformed into a format suitable for machine learning models. It uses the getTokenizer function to extract tokens from the text, and the counter class to count the occurrences of each token. The code iterates through the trained text data, tokenizing each line and updating the token counts in the counter object. A vocab object is then created from the counter, with a min-freq parameter of 2, which means that any tokens appearing less than twice in the training data will be excluded from the vocabulary. The vocabulary is used to map tokens to numbers. For example, happy to own it becomes a vector of 5 numbers. Next, create a function to work on the full training dataset. Our function is called pad_features, and it uses the dictionary to tokenize each review. The tokenized reviews are then stored. Here is an example of a text review being tokenized and converted into a sequence of integers using the pad_features function. The original text didn't give a 5 because I don't know what I need. I like it great is first printed, along with its length of 64 characters. The pad_features function then tokenizes the text and pads or truncates it to a fixed sequence length of 50. The transformed text is represented as a PyTorch tensor containing the token indices, with padding values of 1. The shape of this tensor is 1, 50. Next, generate the batch and iterator to offer the data to the model. You can use pre-trained glove word embeddings. In this example, a pre-trained model is used to generate the word embeddings. The glove 6B model was trained on Wikipedia 2014 and GigaWord 5, and it contains 6 billion unique tokens in its vocabulary. The dim parameter determines the dimension of the word embedding, which is 300 here. There are various hyperparameters for building the network. This includes the size of the hidden state vectors for the RNN, as well as general neural network training hyperparameters such as the learning rate and number of epochs. Additionally, the size of the embedding vector and vocabulary can be defined. The init constructor of the net class from PyTorch receives the hyperparameters, instantiates the RNN layer, instantiated the linear output layer, and instantiates the sigmoid activation function. The forward function is used for prediction or a forward pass. It starts by generating embeddings from the text input, followed by the RNN module to model the sequential data. Finally, a linear output layer processes the output of the RNN module and transforms it using the sigmoid activation for the binary classification task. Before initializing the neural network model, first define the function that initializes the weights. Then, initialize the neural network. This architecture has two RNN layers. The model is instantiated, then the embedding layer's parameters are set by using the embedding matrix from GloveA. We don't change the embedding layer because we are using pre-trained weights. Finally, initialize the weights by using the previous function. After initialization, the output describes the architecture, including the dictionary size, embedding vector size, input size for the RNN layers, hidden state vectors, and number of layers. The linear output layer has an input vector size and output size that are output. The output activation function is a sigmoid function. The linear output size of one associated with the sigmoid function gives the prediction for your classification problem, sentiment analysis. Once initialized, we have the RNN architecture. This slide contains the typical RNN architecture with input layer Xi, output layer Yi, and one embedding layer of 26,300 neurons. The architecture also has two RNN layers with 300 neurons in each layer. Now that the network is initialized, it is time to train. First, define the loss function. Here we use binary cross entropy for the sentiment analysis problem. Then, set up the trainer object that will handle the optimization process by using stochastic gradient descent. This is a classical approach to train a model. It starts by getting the compute device for the model. Then, it enters an epoch loop where training and validation iterations are run on the full datasets for each epoch. The training loop iterates over the full training dataset, optimizing the model for each batch of data and targets from the train loader. Here is where the code to run for each training batch would be inserted. Similarly, for validation, the loop iterates over the validation loader, with a placeholder for the code to run validation on each batch. This alternating process of training on the full training set and validating on the full validation set is repeated for the specified number of epochs. By separating the training and validation steps, this classical approach allows the model to be optimized on the training data while monitoring its performance on unseen validation data at regular intervals. This helps track the model's generalization ability and prevent overfitting during the training process. Details of the training iteration are described in the following code. Optimization steps include the forward pass, loss function calculation, and backpropagation. Details of the validation iteration are described in the following code. Notice that no training occurs, so optimization steps aren't included. Unlike training, no optimization or weight updates occur during validation. The key steps involved are, first, the validation data is input into the trained model to obtain predictions. These predictions are then compared with the true target labels using a loss function, such as cross-entropy loss. This loss calculation allows us to evaluate the model's performance on the validation set without modifying its parameters. The validation loss is summarized for each epoch, enabling us to track the model's performance over time and potentially identify issues like overfitting or underfitting. By monitoring the validation loss alongside the training loss, we can make informed decisions about stopping training, adjusting hyperparameters, or modifying the model architecture. This continues for each epoch iteration. The slide displays the output per epoch for 7 epochs during the training of a neural network. Included is the training loss, the validation loss, and the time in seconds. There are various metrics for classification. You can print the confusion matrix and accuracy score. Remember that a good qualitative shape for a confusion matrix has higher numbers for both values in this diagonal, true positives and true negatives. Next, read and process unseen data to make predictions. Get the predictions for the first 10 data samples. Remember your business problem of sentiment analysis on customer reviews. 1 means positive sentiment, and 0 means negative sentiment. Save the predictions in a simple CSV format file. These files usually contain only the prediction value and the associated ID for each row. The file can be offered, for example, to the client application that will handle the predictions. The next lesson will explore computer vision. Thank you for watching.